All right, welcome back, everyone. My name is Ryan Schul. This is my channel. It's all about data science, machine learning, and things similar to these. Okay, so this is another installment in my environmental protection series. So basically, I took you through 3 other videos. This is number 4, and this one we're looking at regression, deep learning, and neural networks using Python, and we're trying to improve the way that we protect the environment through a bunch of different means, either more recycling, picking up recycled materials in a more efficient way, so finding the shortest path to everybody's house to pick up all the recyclables and get back to the recycling center. I just finished a video about that. I have some videos on clustering, classification, regression, and so on and so forth. So this one, we're going to start with regression and go into deep learning and neural networks. Let me take you through it. So I have a hypothetical data set that I set up. Now, I didn't find the exact data that I really wanted, so I created my own data. So I'm a big proponent of MVPs, minimum viable product, or what's it called? What was the other one? POC, proof of concept, right? Just show something, get something out the door, get it going, get it moving, get something done. I've worked in teams where they try to do everything perfect and they spend months and months, nothing's happening, getting no traction. You're burning through 6 months and 8 months and nothing's done. I really hate that stuff, right? But I've been exposed to that quite a bit. I'm really more a fan of start small, scale up, scale out, make it work. MVP, POC, just get it done and get it going. Okay, so I couldn't find the real data set that I wanted to work with, so I created my own. That was the genesis for this right here. We have city size, population density, average household size, so on and so forth. I don't have to read all the headers to you and spoon feed you all this information, but this is the data frame with a bunch of recyclable related information here and some details about the population, the size of the town, per capita income, energy consumption, so on and so forth, right? So I go ahead and set up my regression model here. I'm going to drop all the columns except for recycling rate percent. So I want to measure what is the percent of people recycling and how can we change this? How can we impact this? And what variables over here, if I look at all the features in my data set over here, city size, population density, emissions, recycling bin, accessibility, what is going to have the most impact on the recycling rate? Okay, so I drop one column. This is going to be my features column or my independent variables. The target is my dependent variable. And I'm going to feed that into this variable right here. I'm going to remove the target from all these other variables. So I'm looking at recycling rate percent. That is right over here. Where is it? Yeah, here, right? So I want to predict recycling rate percent based on all the other variables in the data frame. So I put that into a random forest regressor. I'm not going to go into all the details of the machine learning model because I have several other videos that discuss how this stuff works, but I'm just going to go ahead and run it for you and you can see firsthand how this stuff goes, right? So control enter to run and we get an R² of 0.081. So that's a horrible R². We really want to see 0.70, 70%, higher is better, 0.8, 0.9, 0.95 would be great. We have 0.8. So about 8% of the time, the algorithm is able to predict the target variable, which is recycling rate percentage, is able to predict how many people or what percentage of the population is going to engage in recycling activities in this neighborhood. That's only 8%. It's way worse than guessing. You could probably say 50% of the time, I'm just going to guess. People will recycle, people won't recycle. That's 50-50 chance. Here it's 8%, so it's way worse than guessing. This is basically a useless model, okay? So random forest regressor is not able to help us to make this prediction of what is the actual percentage of recycling in this neighborhood per household, depending on which metric you're looking on. It's basically useless based on this R² right here, and the error rate is about 364, okay? So given the data set, given the model, I tried a few different models, the data set just doesn't lend itself to making these kinds of predictions, okay? But in my last video about recycling, I actually did find a couple models that performed quite well, so you can check those out. It's mostly based on reinforcement learning. It's not based on regression analysis, right? So it's a different type of approach to solve this type of problem. Check out the other video and you'll see the solution. So I just wanted to show you sometimes data science experiments don't work and it's fine, right? It's not the end of the world. We just take a step back, try a different approach, try a different technique. There's a lot of ways to skin this cat to get to the end to achieve the goal that we want to achieve here, right? But this model, and given this data set, is not the way to go. It's only 8% effective. We want to see at least 70%, or this is a no-go in my opinion. And 70% is a minimum threshold even to be granted consideration, right? Like even 70% is kind of low. So 8% just ain't going to cut it. We're going to leave this alone. But we're going to go ahead and look at a different approach here. So I have a different data frame, size of square footage of a house, wall insulation, roof insulation, window type, HVAC, cooling, heating systems, number of occupants in the house, outside temperature, solar exposure, smart thermostat, and energy consumption. So I want to go ahead and not predict who's going to engage in recycling. We know that regression models aren't good for this type of thing, right? But reinforcement learning is. Check out the other video, you'll see why. But we can go ahead and predict what is the amount of energy that this household will consume, right? Based on square footage, all these other features, all these other metrics. I can predict very accurately how much the house is going to consume in terms of energy per month. So like we saw before, we have the features. These are the independent variables. Target, we'll have one target dependent variable, okay? So this is going to be energy consumption in kilowatts per month. The metric is kilowatts, right? So it's a not standard US system. Oh wait, I'm sorry, this is US. I think this is kilowatts is US system. I was thinking of something else like kilometers, sorry, apologize. So standard metric in terms of energy consumption, kilowatts per month. We're dropping it from this data frame, right? Data frame dot drop this column, and we're using it in the target variable. So we drop it from features. We keep all the others. We keep all these features, but not the last one. And then we're measuring the last one. We feed it into this algorithm. This is, we are using what now? Let me look. Random forest regressor. Okay, so we had the random forest regressor over here. I think that was the same, right? Was that the same one? Let me see. Same model. Okay, so random forest regressor here did not perform well, got 0.8, not even 10% accurate. It's only 8%. In this scenario, 97% accurate, right? So mission accomplished, we achieved the goal. We're 97% accurate in terms of our ability to make predictions and how much energy a home will consume based on these features, the square footage, size, insulation, HVAC, temperature, number of occupants, so on and so forth. We can predict with high degree of accuracy how much energy the home will consume. I'm going to set up a brand new prediction exercise right here. So we trained and tested the model. We fit the model. We trained it, tested it, scored it. The score, again, mean square error. The error is 7,190. But it sounds like a big number, but it's actually relatively small because we're looking at the energy consumption. That's what we're trying to predict. And the R² is 97% accurate, right? So this is what you can focus on most of the time, or adjusted R², right? If you want to account for, what is it called? Independent, if independent features are themselves correlated, high correlation, multicollinearity. So I believe the R² adjustment, called adjusted R² appropriately, is going to handle that kind of gotcha. That doesn't happen too often, but it does happen, so you have to be aware of that. So we set up a new prediction here based on what the model was trained on and tested on. Okay, we fit, trained, and tested over here. We set up a new prediction, and we're saying the prediction energy consumption for this house, given 3,500 square feet, wall insulation, HVAC, insulation, smart thermostat installed, so on and so forth, energy consumption, 1,727 kilowatt hours per month. So let's look at, just very generally, just look at one feature just to get a ballpark estimate here. And that actually counts for all of these, right? But just to do a very quick sanity check, 3,500 square feet is the size of the house. This is 1660, about half. You have 7,500 kilowatt hours. This is almost doubled, right? And the size of the house is almost doubled, right? So that kind of makes sense. Bigger house, bigger energy consumer. That's just like back of the napkin, right? An equation on a cocktail napkin when you're sitting in the bar. Quick sanity check. You're done in a couple of seconds here, right? So we'll look at all of these features simultaneously, but just looking at the first one, this makes sense to me. This house, 3,500 square feet, is double the size of this house, give or take, and the energy consumption is double. This is 755. This is 1,700, right? So a little more than double, just over double. And we can go ahead and assign a cost to that energy. It's going to cost about $207 per month for this house to run. The other house, we didn't assign the dollar cost, but we can assume that it's half the size of the house. It's going to be about half as much, $100 per month to provide energy for that smaller house. Half the size, half the cost, right? So let's look at another example here. This is a TensorFlow model. Now this is under the deep learning umbrella. We just saw a traditional machine learning, classical machine learning regression problem where you're going to do the same type of thing using TensorFlow. So this is deep learning. So this performs well. This and its brother PyTorch, TensorFlow and PyTorch perform very well on very abstract, very complicated, nonlinear, fragmented, distorted data sets. It can go ahead and learn the data set very well, learn all the nuances and make predictions very well. This data set actually is pretty structured. We have the columns over here, the data down here, this, that. If we're missing a whole bunch of data, or we had really weird data, or lots and lots of features, hundreds or even thousands of features, the TensorFlow model, or this approach, would probably perform better than the traditional standard regression model, right? But this regression model is performing pretty well. It's getting 97% accurate. Let's see if we can improve the outcome with this TensorFlow model. Again, it's not necessarily the right tool for the job, but it handles big abstract data, complex data sets very well. This tends to be not that complex, right? We only have like maybe 12 columns of data here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 12 or 13 columns of data, right? So let's see how this TensorFlow reacts, and it's creating 50 epochs, and epoch is a loop. So it's going to go ahead and loop through this scenario 50 times. I can go ahead and run it just so you can see how it works. It just spits out the epochs, right, as it goes through these loops. And I made a note here. The model is creating 94% accurate results, right? Okay, something didn't refresh. Let me refresh this. Refresh this one by one. So let me refresh this. I think we did this one already. Let me just do one more. No, we didn't. Oh, I know why I didn't refresh that. Refresh that. Okay, refresh the data set. So that is fed into memory. You can refresh that. Make the predictions, 1756, just slightly different. Each time it starts off a little bit random, so the outcome is slightly more or less. Usually could be the same. That's kind of the exception, not really the rule. So everything is refreshed in memory. Let me go ahead and refresh this. Here's the first epoch, 1 of 50. Basically, an epoch is a loop. So it will run through 50 loops, and you can see over here the value loss starts a little bit high, 25, 079, 24. So the loss that this model is experiencing in terms of data loss or knowledge loss, or just its opportunity to make mistakes, is diminishing quite rapidly over here at the end, more and more and more. And the opportunity for the model to learn is increasing. So the loss is decreasing. The model is learning better and better, 93.9% loss, so 94% accurate. That's just what I showed you over here, 94% accurate. So pretty accurate, but the standard classical regression model was actually even more accurate. This was 97%, but again, this is mostly because the data set is pretty small. We have 12 independent features, 1 dependent, and the data is highly structured, right? If it was unstructured data, the TensorFlow model would probably perform much better. In this case, the classic regression model performs pretty well because everything is just totally straightforward. Here's a cross method. Just like TensorFlow, we will run it on the same model. Again, looking at the overall energy consumption per kilowatt month, we're dropping that column and feeding in the prediction. How much energy will this house consume? So again, creating the epochs, and epoch is a loop. We're going through this 100 times instead of 50. You can see the loss here starts at 1408, goes down to 120 pretty quick. So it's losing less and less information. It's learning. The learning rate is improving, okay, up to a certain point, and then it just can't improve anymore. It's going to make a prediction, and the prediction is going to be pretty accurate at a certain point. We're up to about half of the epochs, and I think, oh, here it is over here. So I can expand that. I was still running. I can tell by the hourglass over here, and we would see an asterisk in the upper left-hand corner of this view right here. So the model is still running. So we're pretty much almost done, I think. What are we up to? 96 epochs. Okay, I think it's done. So I can go ahead and expand that if I click on this, or it doesn't do it. Okay, 97%. So slightly better than TensorFlow, just about as good as the random forest regressor, right? So learning and making accurate predictions up to 97 percentile, so pretty accurate, right? So PyTorch is another type of deep learning technique. just like we saw before, we can go ahead and run this model. We have all the data fed in from the previous two models, the TensorFlow and what was the other one over here? Keras, right? These are all somewhat similar, slight differences, and there's pros and cons to each one. I have some notes about that. This one is making predictions 90% accurate, so not quite as good as the TensorFlow or the Keras, all right, and not as good as the classic random forest, but PyTorch is still performing pretty well, 90% accurate. Nothing to complain about there. Let's look at one example of a neural network model. So deep learning neural networks are kind of based on the human brain, right? You expose an agent to a lot of information, like a child learning. You say, this is a duck. The child learns to associate the shape and the characteristics of the duck with a duck and says, okay, that's a duck. So these models tend to learn similar to that. Classification models are kind of different. Regression models are kind of different, but neural networks and deep learning techniques are similar in terms of the scope and the ability of the model to learn, similar to how a human would learn something. So if I go ahead and run that, Control Enter to refresh the cell, we can see it's running. You can see the hourglass in the upper left-hand corner and a little asterisk in the top left corner of this cell right here. And we can see it's done, produced 95% accurate results. Okay, so they're all 90% or over, pretty decent learning and in its ability to make predictions. I didn't redo the energy example over and over, but you can see it's essentially the same, right? We're predicting energy consumption. We did that once. We don't have to do different flavors. It's the same thing over and over, right? You get the point. And we figured out the cost for this household, $207. So I didn't repeat those exercises. It's the same type of iteration over and over down here, right? So there you go. There's exposure to classical regression, deep learning, and neural networks, and everything was executed just as expected and produced results that, again, meet our expectations. So I have some notes over here comparing and contrasting random forest regressors. So classical machine learning to TensorFlow, that was developed by Google. Think about 10 years ago, give or take. PyTorch came from Facebook about the same time, I think, about 10 years ago, give or take. And I have the pros and cons for each of these machine learning techniques listed here, when to use it and then when not to use it. Okay, so there's some tips where you can absorb that when you have some free time. So I'm going to wrap it up there, guys. That's pretty much it. Hopefully that was intuitive and interesting. Hopefully you learned a couple things. I love to drop knowledge here and hope people get up to speed with things I think are quite fascinating and actually pretty important in our society today. So that's it. I'm going to wrap it up right here, and I look forward to see you guys in the next one. Take care. Bye.